Welcome back to Multigrid Methods. We're talking about the hierarchical basis preconditioner, and we're reviewing work that we did about a month ago, just so that we can be back on the same page that we were previously. I'm not going to do anything having to do with the hierarchical basis preconditioner in great detail. I'm going to try to fly at a very high level and give you this overview of what we've done and just get us back to where we were, I guess. So last time we reviewed the hierarchical basis for finite element spaces, and last time we also got as far as defining the hierarchical basis preconditioner. Uh, Remember, this depended upon these prolongation matrices QL, QL super L, which took these elements from our spaces W and pushed them all the way up to the space VL, which is the space of finite element solutions on the finest possible grid. And we use those to construct this thing called the hierarchical basis preconditioner. Last time we introduced this C matrix, CL, and we argued that that matrix defined through this bilinear form is just going to be the identity at each level, L or J, whatever you want to call it, just the identity. So whenever we take the inverse of that thing, it collapses. And so our hierarchical basis preconditioner is just this object here. QL is, again, our prolongation matrix going from our space WL up to our space V capital L. And so it's a tall and thin matrix. Okay, so it has a lot of rows and only a few columns. And ZLL is the transpose of that. So each one of these guys is a square matrix of size NL by NL. When I multiply these two things together, regardless of what little l is, when I add them all up, of course, I get a bunch of matrices which are all size NL by NL. And that gives me a matrix in the end, which is NL by NL. Okay, that's good because a preconditioner is something that I'm going to apply on the left-hand side through multiplication to the stiffness matrix AL. So I'm going to take my preconditioner defined as it is and multiply it on the left-hand side of AL to give my preconditioned coefficient matrix. Now, I'll remind you of something that we covered in a numerical analysis course here at the University of Tennessee, when we covered the um, the conjugate gradient algorithm. When we covered conjugate gradient, we did all the theory, and then we redid the theory for the preconditioned conjugate gradient algorithm. And I convinced you, I hope, that uh, you know, those of you at least that took my course, and maybe some of those that took the course from Dr. Salgado, that when I use a preconditioner, really what I need to do with that preconditioner is to be able to apply it through multiplication. Okay. So I need to be able to do operations like CH times a vector. Well, that means I just have to be able to know how to do something like this in an efficient way in the computer. Now, last time we talked about why we have what's called an additive preconditioner. That has to do with the fact that this is obtained through addition, not multiplication. So each component is added up. So the application of this preconditioner matrix, when I multiply it times a vector v, can be done in pieces. And the reason why people like additive preconditioners is because I'm able to do these operations in parallel to each other. Additive things can be done in parallel. So for example, if I want to affect this matrix vector multiplication, I can do it via a sum, L equals 0 to capital L, Q L L Z L L times V. And if you like, we can put a V subscript L here to indicate that it's from the fine level space. So what I have to be able to do then in order to do this multiplication, let's break this up into pieces now. So I have to be able to do the first one first, of course. I do 0L Z0L VL plus all the way out to, let's see, I'm summing QLL ZLL VL. So on each, suppose I have a few different processors in the mix here. I can do each one of these operations on different processors if I like. I can do them in parallel, or if load balancing is appropriate, or if I'm able to balance the loads. But in any case, I can do this operation separately from this operation. So really what I need to know is how to do this operation. Now you might think, okay, well that's easy. I'm going to create this matrix in the computer and then I'm going to do matrix vector multiplication. And that is completely wrong, at least from the point of view of efficiency. What I want to do is write an algorithm which applies this matrix to this vector in matrix vector multiplication sense, but done in an efficient way, taking into consideration the fact that there are a lot of zeros in these matrices. So if you remember going back to whenever we were building these matrices to begin with, these QL matrices, they had a lot of zeros in them for the hierarchical basis. So it's not efficient to do multiplications where there are a lot of zeros. What I want to do instead is use the fact that those are zeros and not do multiplication of 0 times something else, and use the fact that structurally when I have a 0, I'm just going to ignore that particular component associated to that. So when I do this multiplication here, I'm going to take into consideration where are the zeros for this guy. And then when I multiply it times this vector, I'm not going to actually do 0 times the appropriate component. What I'm going to do is write an algorithm which sees the zeros and ignores the components for owing to the so let me say that again. I'm going to look for the zeros in this matrix and ignore the components associated to the locations of those zeros, if you understand what I'm saying. So all of these products that are contained here can be done efficiently, and they can be done in parallel to each other, if that's appropriate. So the nice thing about these types of methods is, again, they don't have to be done. I don't have to wait until this is done in order to do this process. I can do them completely in parallel, and then I can gather up all the results together at the end and then add them together in the on the home node of the parallel process. So that's why these things are useful. The other reason why they turn out to be useful is the fact that when I look at the condition number of the preconditioned system, CH times AL, the condition number of this turns out to be, or I can prove that, is significantly smaller than the condition number of the stiffness matrix alone. Let me bring up another point which is quite useful, and that is, well, whenever we do finite elements, the nice thing about the stiffness matrix of the finite element matrix is it's mostly zeros. It's a very sparse matrix, and that has to do with how we chose the Lagrange nodal basis entries and the fact that they are sharply peaked. Okay. Well, that is also kind of a downfall of this method. So whenever I choose a basis like this, it produces a stiffness matrix which is sparse, But the problem is the condition number is really high, really large, especially if the mesh spacing is small. So we've already shown how the condition number depends on the mesh spacing. So the nice thing about the precondition system is, well, it kind of removes that ill conditioning that's associated with the finite element process. The fact that you have a sparse matrix has lots of zeros, but it has a large condition number. When we precondition, we're going to remove that. We remove that ill conditioning, and we bring the condition number down, hopefully to some number which is very close to one. So now I'm going to show you through the rest of the slides today, hopefully, and flying again at a very high level, how this works to give us a condition number which is closer to one than a lot closer to one than the condition number for AL. And why is condition number being small good? Well, uh, in the conjugate gradient algorithm, the convergence rate depends on the condition number. So if the condition number is smaller, then the method converges faster. So if I precondition in such a way as to make the condition number a lot smaller, then my conjugate gradient algorithm is going to converge a whole lot faster. That's the idea. All right, so hopefully that explains why we're doing what we are doing. So again, I'm not going to prove most any of these results that I'm going to claim because you can see how far I've got to get in a short amount of time. I really want to make it all the way to the start of the BPX preconditioner today, and hopefully get a fair ways through BPX preconditioner as well. But of course, we know we're going to encounter typos and errors and things like that in the lecture notes. And let me know if you spot any that I don't. All right, so if assumption SS1 holds, I should say not if assumption SS1 holds, but assumption one SS1 does hold for the hierarchical basis decomposition. So in other words, the Q matrices that we've established through a hierarchical basis um, satisfy SS1. So in particular, what we mean by that is if I take any object, any arbitrary object UL in RNL, and remember these are thought of as the coordinates of the finite element function UL in the finite element space VL. This is the solution that we're looking for in the finest level space. It's connected, these two objects are connected through my choice of bases. I'm using the canonical basis, the Lagrange nodal basis for my space V. Notice that I have to use this superscript V because I also have a basis for my W spaces, which are the hierarchical basis spaces. Let's see. Not exactly the hierarchical basis. So hierarchical basis is a specific thing when I take a union of these guys. So this is just the basis for this space. Okay, so if I take any object here, then there exists unique objects WL in RML, which is connected to some finite element function in WL. Remember, these spaces are those spaces where it's like VL, except that I remove the degrees of freedom associated to nodes that are in the coarse mesh. That's exactly this space here. So WL is VL with some degrees of freedom removed, specifically those that are associated to VL minus 1. So we had a basis for that. Okay, so there are these unique objects such that UL is equal to the sum of the WLs. Okay, and of course, I can write that either in the finite element setting or I can write it in its coordinate setting. So the coordinates are UL is equal to the sum L equals 0 to capital L, QLL, WL, which is an element of RNL. Let's make sure that all of the dimensions are correct here. So remember, QLL is a tall and thin matrix. So it has NL columns and it has capital L, I should say. So it has QL. L is a matrix which has NL columns and it has m little l. Did I say that right? I think I said it wrong. NL rows and m little l columns. Okay, so this number is much bigger than this number, so it's a tall and thin matrix. This is a vector which is small. It's from RML, but when I multiply it times this matrix, remember this matrix, as I just said previously, has a lot of zeros in it, kind of padding things. And so this guy expands the size of this and sort of stretches it out to a vector that has a lot of entries, NL entries. And then finally, I can add things together to get U sub L. Now, why is this true? Why do I have these unique objects? Well, this is just a fact that says, this is just a fact that uses the fact that the hierarchical basis is a basis for VL. Okay, so the hierarchical basis is slightly different than the Lagrange nodal basis because it reuses and recycles basis entries or basis elements from the course spaces. And it's basically just that fact. It's a restatement of that. The fact that I can have this hierarchical basis decomposition gives me this fact, end of proof, end of story. I don't have to really do anything. And that's of course, guarantees that assumption SS1 holds. So in the first slide deck for chapter 9, we said there's all of these things that hold because SS1 holds, and so now we can invoke those. So now what I want to do to establish the result that I want to get is ultimately I want to show a lower bound for the smallest eigenvalue of the preconditioned stiffness matrix. This is the preconditioned matrix here, or preconditioned coefficient matrix, CHAL, is greater than some constant times this thing which depends on log, which I'll explain in a moment. And I want to show an upper bound for lambda max for the same system, which is a constant and independent of L entirely. So this one, unfortunately, has a slight L dependence, which I wouldn't otherwise want, but I'm gonna deal with it because it's gonna turn out not to be all that bad. So now if I put these two estimates together, I want an upper bound for the condition number. And the condition number for this matrix, the new preconditioned coefficient matrix, is just the ratio of the eigenvalues, lambda max over lambda min. And if I really can establish these two results, then my condition number, lo and behold, is less than this number. Well, this number I want to guarantee is not that large. Well, let me get rid of some of your worries. So this number here is independent of L, and it's not all that large. You can think C here is equal to 5 or 10. It doesn't matter. It's really pretty tame, pretty small. So the thing we worry about is this guy. Well, everyone knows that the log, it can be problematic going in either direction. Either if I'm putting small things in, right, this thing is blowing up to minus infinity, but if I put large things in, it's growing. But actually, it's not going to grow all that fast. So this guy here, HL, is a small number, and we should think that number is smaller than 1. So that's why these absolute values have been applied here. So it looks like, okay, so HL is getting small. So this guy's, oh, that's too bad because this guy is going to blow up, right? So really what this thing looks like is that, right? When I take the absolute value. But actually it's not too bad. It's not too bad because let's look at what HL is typically. So HL is something like 1 over 2 to the L. Right? So every time I do a level, my mesh spacing gets smaller by a half. And this is a result of the fact that my meshes are nested, and the refinement process that I use is bisection or quadrisection in 2D. All right, so it turns out then if I use the fact that HL has this form, then absolute value HL of log HL squared is not too bad. It's something like L squared, and that the L comes out, right, of the exponent and gets squared because I'm squaring this. So I have an L dependence, which looks like this. And now log of 1/2, that's a number which is, whatever it is, it's a number, half is less than 1. So log is a negative number. I have to take the absolute value and square it. But that's a fixed number, which is completely independent of L. So this number here only goes to infinity, and it has to go to infinity as L squared, which isn't too bad because remember, L is like the number of levels that I have in my mesh. So I may only have 5 levels or 6 levels, or at worst, let's say 10 levels. So if it's 10 levels, I said that this constant is like 10. And so this constant here, which is going to depend on L, is like 100, right? Because I have 10 squared. 10 squared, 100. So I have 101. So roughly speaking, this is 10 times 100, so that's 1,000. Is that bad? It's not the greatest thing because remember I was promising you the world when I said that this condition number was small. It's not like 1, it's not like 2 or 10, it's more like 1,000. Is that bad? Well, actually not too bad because if I think about how bad the original stiffness matrix condition number was, this thing could be like in the millions or billions or trillions. Okay, so it could be really, really large. And so I'm doing pretty well getting it down to 1,000. This isn't the best I can do, but it's not too bad either. So now let me preface this by saying this analysis, and it looks like I'm going to do a lot of analysis here for, I'd love to do more gain. I'd love to get more gain out of this, but the analysis is only going to work for 2 dimensions. It doesn't work in 3 dimensions. Actually, the story is a little bit better in 1 dimension. In 1 dimension, I can get rid of this altogether. But then again, 1 dimension is not that interesting because, if you think about this problem, the stiffness matrix is already a tridiagonal one, and there are fast tridiagonal solvers that you could use. Although Calvin, one of my students, will attest that just because you have a nice tridiagonal solver, you shouldn't assume that it can get an infinite amount of precision for you. So there are other methods which turn out to be even better than a fast tridiagonal solver, it turns out. But in any case, we're going to do this analysis for d equals 2. And then we don't get everything in this analysis, but we get something. Now, the analysis we covered last semester in December of last year, and this is just supposed to be a quick, and I put quotes around quick because I talked too much, a quick review of what we did last time. Well, we needed a bunch of technical lemmas in order to prove the lower bound for the lambda min and the upper bound for lambda max. And so let me review some of these because I am going to come back to these and we are going to use them whenever we talk about the BPX preconditioner. So what are these? So the first one that we're going to need is what's called the mean zero Poincare inequality. And it goes like this. So if I have U in H1, so notice I'm not putting any boundary conditions on this guy. So normally I would say the boundary conditions would be U is equal to 0 on the boundary, blah, blah, blah. So I would look at the subspace H1, 0. But now I don't want to do that. I want to be more general. And I want to look at omega being an open polyhedral set, something very general, not necessarily a triangle, not necessarily a square, something polyhedral. Remember, polyhedral simply means I can put a triangulated mesh on this object, on this set. Well, there exists a C such that the difference of U minus its mean, so this means the mean of U, so this is a constant. U minus its average or mean measured in the L2 norm is less than a constant times the norm of the gradient of U L2. Remember, this is like the H1 semi-norm piece. This constant, what does it depend on? It has to be independent of U. However, it will depend upon the shape of omega. It'll depend on the shape of omega. How is the average defined? The average is defined the way it usually would be. You divide by the size of the domain that you're working on. So that's the measure of the domain. So if it's a square, it's the length times the width, right? And then you take the integral of that function over the domain without absolute values or anything like this. You want the absolute, or you don't want the absolute. You want you want the straight average, okay? So this is what is called the mean 0 Poincare inequality. Now, do, do you remember it? That's the question. Have you seen it before? Some of you have, if you've taken PDE. We always prove this in my numerical analysis class in the second semester, which here at the University of Tennessee is 572. So we always prove this at least in one dimension how this works. So you may or may not remember it, but this is something that we're definitely going to need later on. Okay. Now, if we have this, remember the H1 norm has an L2 part and it has a gradient part. So the full H1 norm is an L2 part plus a gradient part. Well, I can break the H1 norm into its L2 part and its gradient part. Well, the L2 part is going to be bounded by something which looks like the gradient part, and the gradient part is already the gradient part. So this is like saying that u minus u bar can be bounded by its gradient part alone. Okay, so one of the consequences of the Poincare inequality is that u minus u bar in the full H1 norm is bounded by a constant times just u in the semi-norm. Okay, so we're going to use that somewhere. We're also going to make use of inverse inequalities. So we've talked about inverse inequalities last time. We've talked about inverse inequalities in chapter 6. This one is a fairly general inverse inequality. And now inverse inequalities, just if I'm giving you a high level picture of what's going on with them, is I can never, I can generally never bound an H1 norm by a lower L2 or LQ norm, LP norm, something like that. This guy usually is what beats this guy, okay? But in a finite dimensional space, when I'm working on something like a finite element space, those are all finite dimensional. Like for example, this space SL or VL. VL and SL are the same spaces. VL differs from SL only in one point. So VL is SL, but where I restrict the functions to be 0 on the boundary. So let me write that out. VL is just equal to the finite element functions in SL such that when I restrict them to the boundary, they're identically 0. Otherwise, they're the same functions. But they are finite dimensional, no matter what. They're finite dimensional spaces. Well, for finite dimensions, remember, all norms are equivalent. So if I produce a norm, it's equivalent to any other norm that I want to choose, right? But the point is, all norms may be equivalent, but I may have to pay the price of the dependence of a dependence on H, okay? And so these are what are called inverse inequalities. When I try to control a heavier norm with what's called a lighter norm, I have to pay the price of incurring these these uh, these coefficients here, which depend on HL, the mesh spacing, and they can depend on the mesh spacing in a kind of bad way, namely these HLs, by virtue of the fact that I have negative numbers here, appear in the denominator, so that as HL gets smaller and smaller, this constant blows up. Okay. So remember, in finite dimensional spaces, all norms are equivalent. However, what I'm interested in when I'm talking about PDE is making that mesh spacing smaller and smaller and smaller and smaller. And so I have to pay attention to how the constant, so this is the full constant, depends on the mesh spacing. Well, if I'm trying to control a heavier norm with a lighter norm, then I'm going to have to pay a price which looks like this. And this is called an inverse inequality. Now, in 572, we do prove things like this. I'm just going to punt and give a reference, and the reference I'm going to give is a famous book by Brenner and Scott on finite element methods. In the fall of 2025, coming up, I'm going to teach a course on finite element methods, and not from Brenner and Scott, but sort of inspired by Brenner and Scott, based on some notes that I have written up. And we're gonna use this inverse inequality a lot more, and we may even prove it there. In fact, yes, we will prove it in that class, but not here. It's too much. We're simply going to use that. Here's another one. So this is what's called an interpolation error estimate, but it's a really, really kind of non-standard interpolation estimate. And here's how it goes. Suppose I want to measure the error in interpolating a finite element function, but I'm going to use the interpolant at the at the space which is just coarsened uh, to the space where this function lives. So this space VL, the VL, that's a finite element function which lives in the space capital VL. Okay, that's a finite dimensional finite element space. What is the action of this guy here? Interpolant going to L minus 1. Well, that takes any function which is continuous. Okay, so it's a C0 on the space, and that's going to push it down by interpolation to the space VL minus 1. So that means when I apply this interpolation or interpolant to this function, it pushes it from this space just down to the next coarser space below. Okay, so you might think a mesh and its coarsened mesh, or a mesh, a finite element space, which is derived from a mesh, and the one just below it on the coarse level are not too different, right? So I could expect the difference between this function and its interpolant at the next lower level shouldn't be too different from each other. So I can measure the error between that, and that's exactly what these are. This is the error of those two functions. This one is at the space VL, and this guy is at the space VL minus 1. I want to measure their difference in the L2 norm. Well, this is something normally that if you look back in chapter 6, I had a result for this, but when we looked at that result in chapter 6, this function had to be an H2 function. In fact, I had to say it was C2, and it also had to be an H2 function. So I had to say not just C0. I'm sorry, I said C2. I meant to say C0. But I also need it to be in H2. It has to be smooth enough. And then when I apply the error estimate for this guy, it's going to involve the H2 seminorm for that original function. The problem is the H2 seminorm for a function VL is not defined because this function is a finite element function, and the H2 norm requires enough smoothness to calculate the H2 seminorm. Well, that's just not available to us because this function has cusps, right? Or not cusps, but it has kinks. That's what a finite element function looks like, right? So it fails to be to have a weak second derivative at those points. It has a weak first derivative of those points where you have those kinks, but it has no weak second derivative. So I have to come up with something else whenever I do an error estimate like this. Well, the error estimate I can obtain is going to be first order in H. You know, this constant is something which is independent of L, and maybe it depends on the shape of the domain, etc. But it should be independent of H and L, and it should be independent of V. And I I I don't get second order, which I got in the in chapter 6 whenever I had this. I don't get second order, and I don't use the second Sobolev seminorm. I get first order, but I can use the first Sobolev seminorm. Okay, so This is an interpolation error estimate, which is non-standard. Now, the reason why it works is because I'm, again, in a finite dimensional space. Actually, I'm dealing with a very special set of functions. So this would not work in general for a general set of functions in H01. So let's say if I replace this by general functions in H1, then it wouldn't work. However, since I'm working with finite element functions, this interpolation error estimate works. So that's another technical detail that I need to prove the results that I need. I didn't have time to bring out this level of detail when we reviewed this in December, and so that's why I'm kind of going through it here. So whenever I refer to this proof, we don't have VL and H2, so we don't have the usual chapter 6 error estimate. We have to do something a bit different. And so in the exercises, I do ask that the student who dares attempt them, that you prove this in the one-dimensional case. It's actually not too bad. All right, now, what else do I need? So many of you have taken PDE, have heard of these types of results. They're called embedding results. And so an embedding result is written like this, and so this has a twofold meaning. If I have a function which is in H1, then that function has to be in LP. Okay. In two space dimensions, I'm guaranteed that this is true for any p between 1 and infinity, but not including infinity. It includes 1, but not infinity. So what that means is we can't quite get a hold or get control of the case where we have L infinity here. So the other meaning is that, so that's the first meaning. So usually it means I have H1 is a subset of LP. And the second thing I have is that if I have a function that's in LP, there's a constant independent of U such that I have this type of inequality. Okay, so this norm H1 appears here, and so this is a heavier norm, and this is a less heavy norm here. So this is what's called an embedding result. So there's a debate in the community whether embedding begins with an E or begins with an I. I guess most people use E, embedding, EM, B, and so on, embedding result. Now, this does not hold, this does not work if P is equal to infinity in 2 dimensions. However, again, you can see if I go to a finite dimensional space, then I can get that result to work. However, this constant here is no longer going to be independent of the setting. It's going to have an H dependence in it. So here's what I mean in the final analysis. Suppose I have an open polygonal domain in R2. This result only works in R2. Suppose that I have a nested triangulation, as usual, of the domain omega. It goes from the coarsest level up to the finest level. Coarsest level is 0, finest level is capital L. Then for any VL in capital VL, I can control the L infinity norm of VL by the H1 semi-norm of VL, but I have to pay the price of some sort of logarithmic dependence on H, okay? Some dependence on L, and that dependence on L comes through the logarithmic dependence on HL. All right, so this is a rather famous and well-known result. I'm not going to try to prove it because it's complicated. It works for finite dimensional case. So if I have VL and VL, it also works if so this one, remember, this VL is the same as SL, except on VL, I impose the boundary conditions have to be equal to 0. It also works for the case where I don't have boundary conditions imposed, but then I have to subtract off the mean in order to get this same result. Okay. Right. So, and the mean is defined through the usual way. We're not going to prove it, but I just want to point out this result. This result is the one we need, and we're not going to prove it, but this is what brings about that logarithmic dependence that you see in our condition number estimate. And this dependence here is just derived from that previous one. So this is a lemma which is just a follow-up of this theorem here. So it's just a slight rebranding of things, or a slight rewriting of things. So I'm going to skip that one. So the final estimate that we need, the final technical result we need, is some other type of interpolation result, which I'm also going to skip, but it basically is related to the difference between two interpolants, one is at VL and one is at VL minus 1. But I do want to emphasize what's going on here. So remember, IL takes any function. It only has to be continuous, and it's going to push it into VL. Well, that means that IL minus 1 takes the same function and pushes it into VL minus 1. So what we're interested in this estimate here, this technical lemma, is I want to take the solution, or this thing I'm interested in, this finite element function on the finest level grid, and I want to compare the interpolant at level VL with the interpolant at the next coarser level VL minus 1. Okay, so now you look at those two objects and you say they're probably not all that different from each other, because one is at level VL and one's at the next coarser level. And those two levels, those two meshes, look fairly similar to each other. So I would expect then maybe, okay, this makes sense. I'm going to get a constant times HL, the first power, because I'm measuring the UL in the H1 seminorm. Fine. But the surprising thing here is that I also get an extra little dependence that I wouldn't have before. So if I compare this result to the previous one that I had, namely this guy here, there's no extra L dependence. There's only one HL and nothing else. But if I'm not comparing this guy with this, but instead I'm comparing two different interpolants, I have to pay this extra little price. Okay, so I'm going to skip the proof of that as well. Also not too bad. Now, finally, we come to the result that we need. We're not going to go through this proof at all, but we want to estimate the minimum eigenvalue of the preconditioned stiffness matrix CH. CH is our preconditioner times AL. AL is the stiffness matrix for the finite element problem that we're solving. Remember, we're using finite element, so we have this PDE, and we're using finite element, FEM, and we're discretizing, blah, blah, blah. And then ultimately, we are converting this into a matrix problem. Remember, we said there are good things about this matrix problem and bad things. Good thing is AL is a matrix which has a lot of zeros in it. We call that a sparse matrix. But the bad thing is it has a large condition number. And in 2D, it's a rather large matrix, especially it gets larger and larger as HL gets smaller and smaller. Well, we might want to have a really um, accurate approximation of this guy. So we might want our mesh spacing to be really small, so the condition number could be really, really bad. So I'm preconditioning by multiplying a preconditioner times this system, and then I'm going to use something like the conjugate gradient method to solve this. So I want to show the condition number is small. It's precisely because I have this weird logarithmic dependence for this 2D case, um, in that control of the L infinity norm, that at the end of the day, I'm not able to get this constant over here independent of L. Okay, I have to pay the price of some logarithmic dependence on HL. And this comes precisely because of this estimate right here. Okay, so the at the end of the day, it's really all due to this fact right here, that I have to pay the price of this logarithmic dependence. I don't like that, but it's the best I can do when I'm working with the hierarchical basis. I have to pay this price. So this proof is long and complicated, but it uses all the technical machinery that we built up to that point. it finishes off in the end using this theorem, which we derive very simply in the first slide deck for chapter 9. So remember, this is our modified Rayleigh quotient result from the first slide deck from chapter 9. And so the one we're using is precisely this one when we're trying to minimize or trying to find a lower bound for lambda min. So that's the one we use. And the reason why we can do this is because assumption SS1 holds for our hierarchical basis. Why would we use something which looks a whole lot more complicated than the Rayleigh quotient result that we would normally use? And the answer is because it makes life a lot simpler for us. So try doing the same estimate without this result. It's quite hard. I will point out one thing though. When I'm using the hierarchical basis, I don't really have to worry about this minimum here. Okay. The reason I don't have to worry about the minimum is because when I invoke this object here, there is no minimum required because there's only a unique there's only one element in the Q class for U. There's only one element, or there's only one collection of vectors WL in that Q class. And that's because for the hierarchical basis methodology, we have unique representations in the hierarchical basis. And so this min disappears and I can simply replace this. I can get rid of that. Okay, so it does simplify a bit. All right. So now to get the upper bound, I have to use another technical lemma. So it's some sort of convolution result, which we're going to come back to later, but I don't want to get into the details of that. It's rather tricky. It also depends upon something we call a strengthened Cauchy-Schwarz inequality. We're going to use this when we talk about the BPX preconditioner. So I want to talk a little bit about this, and I want to talk about a modified version of this in just a minute. So why is this called a strengthened Cauchy-Schwarz inequality? It's called strengthened Cauchy-Schwarz inequality because it gives more detail about the structure here of the difference in levels for these two functions. So here's the statement. Suppose that VL is in capital VL, so that's one finite element space, and VK is in another finite element space, where L is greater than or equal to 0, but less than or equal to k, which is less than or equal to L. So this guy is the finer space here. This is finer. This is a coarse finite element space. So I'm comparing two different functions at two different levels on the hierarchical mesh. Okay. So one is from the fine level space, relatively speaking, fine level space VK, and one is on the coarse level VL, relatively speaking. All right, so those are the two functions where they come from. They're arbitrary otherwise. They're on those two finite element spaces, but otherwise they're completely arbitrary. Don't care what they are. And again, we're in two dimensions. There is a constant c such that the integral of omega of the gradient VL dotted with the gradient VK. So this looks like the standard inner product between two functions, but they're on two different levels in the H1 space, okay? So sometimes this is called the H1 semi-inner product, okay? The H1 semi-inner product. If VL and VK are the same, then of course you can see it's the H1 semi-norm squared, okay? But right now, these are two different things, so H1 semi-inner product. Not the full inner product, but only the semi. Only that dealing with the highest order component. Well, if this was just a normal Cauchy-Schwarz, we could apply this and we would get H1 semi-norm of VL and the H1 semi-norm of VK, but we wouldn't get any other information. So this gives us more information about the structure of the constant whenever these functions are coming from different levels. So notice that this guy is L minus K is a negative number because L is smaller than K. So this 2 ends up in the denominator effectively. And so this number gets larger. Let's see, 1 over 2, and the number is positive. So the whole number actually gets smaller because L minus K is going to be a negative number as the difference between L and K get larger. Okay. So now what is this guy here? Well, this guy here can be thought of, I'm not going to get into the gory details of this, but this can be thought of as like an H1 seminorm for VK, but don't worry about it otherwise. So this is what's called a strengthened Cauchy-Schwarz inequality. If I apply this now to functions that are in WL, I can get something a bit similar. This is what is used in the proof of the upper bound for the for the lambda max. Okay. Again, I'm not going to go into these details because it's just too many details. All right. So whenever I'm going to prove this upper bound for lambda max, I notice now I don't get any dependence on capital L, which is a good thing. No log dependence, nothing worse than that. And so what technologies or what tools am I using to get this upper bound? Well, again, I'm going to use the fact that I can decompose any vector that I want from the fine level space into W's from the hierarchical spaces. I'm also going to use my strengthened Cauchy-Schwarz inequality, which was 18. And then I'm going to use the definition of my C matrices, which is from 13. Cauchy-Schwarz inequality again. And then I'm going to follow up with that Rayleigh quotient result that I had previously. And what I get in the end is a constant upper bound for lambda max, which is entirely independent on capital L. So we put those things together, the lower bound for lambda min, the upper bound for lambda max, and then we ultimately get the condition number estimate that I stated that we were looking for in the first place. Again, we didn't want to go through all the details of that because this is kind of things that we more or less did last semester. Uh, Actually, if you remember, to be honest, we got hurried through it and we didn't get to go through that in the detail I wanted. But I didn't want to go back and chew through all those details. I just wanted to state them at a very high level. Um, but you can see we get this estimate in the end if all the details are correct, which I believe because um, well, I went through them number one, and then number two, they were published uh, and uh, and it's a well-known result. It is possible that thousands of people have gone through the proof and missed exactly the same errors, but I doubt that. So I do believe the result. But you can see that I get this log dependence, which isn't the best in the world. I argued that this is kind of like for 10 level mesh, this is kind of like 1,000. So it's not as good as it could be, but it's not the worst it could be either. If I'm dealing directly with the stiffness matrix, I could have something which has a condition number in the millions, billions, trillions, something like this. So getting that down from 10 to the 6th or 10 to the ninth or worse, I'm getting it down to something which is 10 to the third power, which is a whole lot better. So the next topic I want to talk about is the BPX preconditioner, and that one is a little easier to analyze, which makes sense just from what you see here. There are a whole lot fewer slides that are required. Okay, so let's get into the BPX preconditioner. BPX preconditioner stands for, or it's the initials of three people's last names. I think it's Bramble, Pasiek, and Shu, but don't quote me on that. I'll leave a reference in the book. Actually, it's I should have a reference in the book, and I don't. I've referenced Brenner and Scott because that's where most of this material is coming from for the proof of this. But the original the original idea comes from these three mathematicians, Bramble, Pasiek, and Shu. And so it's called the BPX preconditioner for that reason. It has slightly better performance than the hierarchical basis preconditioner, uh, but it has some drawbacks as well. Um, so the nice thing is that we don't have to deal with this logarithmic dependence anymore. In fact, what we're going to show is that the condition number for this preconditioned system CBPX AL is less than a simple constant, no dependence on L, completely independent on L, independent of L. And so this guy really is like 10, okay, or 100 or whatever it is, or 20. It doesn't get worse as L gets larger. And so this is quite nice for that reason. However, it's a little bit more complicated to apply and deal with. So, and we'll get into that in a minute. So that's where all the details are for this method. Okay, and so in 15 minutes, maybe I'll get halfway through this section and then we'll leave the other half for next time. But I do want to cover the details of this, at least mostly, I think. Um, so how do we define this BPX preconditioner? Well, like the hierarchical basis preconditioner, it's first, the definition starts out using what we call a bilinear form, CL. And so I'm using the same notation that I use for a hierarchical basis, but it's not the same CL. Okay. So just keep that in mind. This CL takes finite element functions from VL cross VL and maps them to a real number. So it is a bilinear form in the usual sense. It is not necessarily, at least on the first face value of it, an inner product, but it is a bilinear form. So how do we define it? So you take two functions from this finite element spaces, and what we're going to do is we're going to evaluate those functions at the nodes of VL. Remember, these are the interior nodes of the triangulation. The reason why they're not on the exterior is because there are no exterior degrees of freedom for functions from this space VL. All those degrees of freedom are set to 0, so they're not degrees of freedom at all. We don't have to really keep track of those. So these are all the interior nodes of the mesh. We evaluate these functions at the interior nodes, and then we're going to sum them all up over all of the degrees of freedom in the interior mesh, in the interior nodes of the mesh, which are in number NL. So we sum from I equals 1 to NL. The associated matrix for this, we're going to define a matrix by using a basis. Okay. Anytime you have a bilinear form, then you can define a matrix via a basis by just throwing in the basis elements for these two individual spots. So the way we're going to do this is CL is going to be defined by putting in the basis element psi Lj and psi Lk in the first and second entries respectively. But you notice if you do that, then these guys are just the Kronecker delta symbols whenever I evaluate those at the nodes. That's just how they're defined. So when I multiply the two together and sum them up, I get again the Kronecker delta symbol, delta JK. So this again, this matrix, what matrix has the rows and columns or the entries equal to the Kronecker delta symbol? Well, that's just the identity matrix. It has ones in the diagonal, that's whenever j and k are equal, and it has zeros in the off diagonals, that's whenever j and k are not equal. So this is just the identity matrix once again. And I just wanted to point out in my notation here, these are the basis elements for VL. Before, when I'm talking about hierarchical basis, there were two bases floating around. So I had a W and a V as superscripts. I can drop this V now in the superscript because there is only one basis. I'm going to drop the hierarchical space of functions, W's. And so I don't need the W anymore, so I don't need the superscript at all. I'm just going to use the standard Lagrange nodal basis for the piecewise linear finite element space VL. So the BPX preconditioner is precisely equal to sum L equals 0 to capital L PLL, little l, capital L, CL inverse, that's the matrix that I just defined here. Of course, that is equal to the identity, so the inverse of the identity is just equal to identity, times RLL. Okay, so that's the identity, nothing there. What is PLL and RLL? Those are the multi-level prolongation and restriction matrices that we introduced in chapter 8. So these guys were introduced in chapter 8. Okay, so chapter 8, we talked about these multi-level restriction and prolongation matrices. And all these they're obtained by stacking prolongation matrices. So what you do is if you want to prolongate from this coarse space little l up to the fine space L, so you might have a ton of spaces in between. So you've got to go from L to L plus 1, L plus 2, and all of, well, not all of a sudden, but eventually you get to L. So what you do is you prolongate to that space, then you prolongate to that space, then you keep going, and finally you prolongate up to where you get. Now, all you have to do this is we can build these guys independently through the just multiplying these matrices together. So we can take the action here. This is a standard prolongation matrix. This is a standard one. And I can stack them all up, multiply them together, and I get these what we called multi-level prolongation matrices. And the restriction matrices were just going in the opposite direction, right? You just go the other way, and these were defined through the transposes of the prolongation matrices. Restriction and prolongation from chapter 8 were defined in that way through transposition. So these are just multi-level prolongation and restriction matrices that we derived in forgot to say it, chapter 8. Okay, so those are things we've seen before. So here's our BPX preconditioner. Doesn't look a whole lot different than the hierarchical basis one. But these objects are somehow a little bit more familiar to us, right? We know what they look like. The problem is these guys are not things we might have lying around. We have to build these matrix objects. And they may not actually have quite as many zeros as the matrices from the hierarchical basis case, the so-called Q matrices that we had. So in fact, these guys could be fairly complicated. We don't know what they look like. We've never actually looked at them. We've looked at the Q matrices. We've looked at these prolongation and restriction matrices when we're just going from one level to the next. But we've never looked at what these guys look like as multi-level objects. What do these matrices really look like? Well, it turns out they can have a lot of non-zero entries, which in kind of way is bad because when you have a lot of non-zero entries, it means you have to do a lot of work to do these multiplications. Now, remember what we said earlier, when we have a preconditioner, the important thing here is it's going to be an additive thing. When you take a preconditioner, what you need to do in the setting of precondition conjugate gradient is to multiply the preconditioner times a vector. So I have to do matrix vector multiplications in a fast, efficient way. Well, here, those multiplications that we're going to have to do, matrix vector multiplications, might not be quite as efficient as they would be in the hierarchical basis setting. So that's a trade-off, right? The ones from the hierarchical basis setting were simpler and maybe probably faster to implement. And here, these objects are more familiar, but they might have more ones than they have zeros in them. They might be kind of dense looking. We don't know yet. But at least they look like they might be rather complicated objects, a little bit more complicated than the hierarchical basis setting. Right, so why would we pay an extra price to do something? Well, the reason why we might pay the extra price is because ultimately we're going to show that the preconditioned system in this case is, as I said before, has a condition number which is a lot smaller than the than the hierarchical basis one. So the added cost that we pay up front might reap dividends in the end. In other words, we pay a little bit extra now to get have a little bit less cost in the end. So the question is, will this trade-off pay off, right? Will this trade-off pay off? Is it worth doing it? Well, this is only something that you could answer if you could figure out how many floating point operations you might have if your mesh looks like a certain mesh. And so you might have to really do um, a computation in this case. But now the other thing I want to point out with these preconditioners is we talked a lot in 571 about where do good preconditioners come from? How do you construct preconditioners? So they don't simply grow on trees, right? They are not simple things. They exist, but you can see all the theory that we have to uh, derive just to define them, not to mention all the theory we have to derive to analyze them. So, um, so good preconditioners aren't simple things. They take a lot of work, they take a lot of thought, uh, and their analysis is quite complicated. Now, the nice thing here is, of course, maybe we're paying a little extra cost when we do matrix vector multiplications, but the analysis is sigh of relief a lot easier than for the the hierarchical basis one. So just a note, and I've already mentioned this, we're dropping the superscript V that we had on these bases because we no longer have bases for the W spaces floating around. We don't need those, and so we don't need the distinction. And so since we don't need the distinction, it doesn't there's no confusion if we drop that V. Now, in the hierarchical or in the BPX framework, if you're looking for how it connects to the general theory, well, the Q matrices that we need in order to invoke the theory from the first slide deck, um, we need to be able to identify what those Q matrices are. Now we have identification for them. They're just these multi-level prolongation matrices that we introduced from chapter 8. But the questions remain, can we prove SS1, right? Can we prove that it's a stable or what did we call SS1, a subspace actually I forget what name we had associated to SS1, so I'm just going to say, is assumption SS1 still true? I think it was stable subspace decomposition, but I can't remember now. What what did SS mean? Ah, okay, well, it's in the book and it's in the first slide deck. Assumption SS1 turns out holds for the BPX framework. So that is, if you give me any UL and VL, then there exists VL and VL, hierarchy of them, or many of them, from L between 0 going all the way up to capital L, such that UL is equal to a sum of those guys. Or equivalently, actually, that's kind of a triviality, really. Um, can you write a finite element function as a decomposition of a bunch of finite element functions from this hierarchy of spaces VL? Well, there's a trivial one. First of all, there's really one that's trivial, right? We could just take all of them to be 0, except for we could take V capital L, that is whenever little l is equal to capital L, and just set that equal to UL. So we can easily find a trivial representation for this. Just take all these guys equal to 0 except for, so just take this identically 0 for L equals 0 to L minus 1. And then we're going to take VL equal to UL. That works, right? So that's pretty easy. But there are also there are also non-trivial ways we can do this, right? As well. And you can imagine how that might work. Well, the other thing I might say is the other one that can work is that hierarchical basis representation that we found before will work here as well. So whenever we define hierarchical bases and hierarchical method, we define these WL creatures. So we could just take VL to be equal to those WL creatures that we defined previously, L equals 0 all the way up to capital L. And that one will also give us a decomposition which fits nicely into this framework. That's because each VL being equal to WL is in the space WL, but each WL is a subspace of VL. Remember, this guy has degrees of freedom, which are kind of removed by deleting degrees of freedom from the coarse level space VL minus 1. But in any case, these objects do live in this space. So this one works as well, a hierarchical basis decomposition. So that kind of proves the theorem right away. Um, so there's two objects there, so this decomposition is not unique. So that exercise is done for you. Now, we need another strengthened Cauchy-Schwarz inequality. So this one I'm not going to prove. It just follows from that previous strengthened Cauchy-Schwarz inequality that I mentioned earlier, which also didn't prove. Or maybe we did prove that last time. I can't remember if we proved that in December or not. But in any case, this one is not too difficult to prove from that strengthened Cauchy-Schwarz inequality of 17. So we're going to skip that. What this does in strengthening it, quote unquote, is that it measures the difference that we're going to get between these that's accrued by having these differences in these levels J and L. So let me see, there's a question in chat. Okay, SS means simply subspace. Okay, cool. S for sub and S for space. So that's what SS means. Subspace. Subspace property number 1. So later on in chapter 10, the reason why I got confused, we will describe something called a stable subspace decomposition. Uh, and so I thought maybe it's because it's stable, but no, just subspace. Thanks for that in the chat. Okay, so now our min and our max eigenvalues can both be approximated without any dependence at all on L. And so we can't, I'm 1 minute over, so I'm not going to start this proof. This is where we'll start next time. Start here. So we want to go through the details of why this can be done without any L dependence. Actually, it's fairly similar to the hierarchical basis case. And why, when we do the lower bound, we also don't get any L dependence. So it's this one, it's always the lower bound seems, which is the harder one. The upper bound is the easier one. Those are fairly similar. So this guy is for this is a clear typo here that I'm going to have to fix. Okay. C is not just greater than it's supposed to be C sub 10 is greater than 0, but okay, we'll fix that next time. Okay, I'm going to stop there. And you guys can turn your cameras back on and I will take any questions you have. Questions, comments, reactions, disappointments. Everyone's good. I got one good person. Yes, she's good. Everybody, oh, another good person. Got lots of good persons. Yes, awesome. All right, so you can see I'm going to give the details of this BPX preconditioner, but I'm also trying to say a lot more about implementation issues, even though in this chapter, We don't have an implementation in code, which is something to be nice to fix or address in the future. But I don't see it happening before we get through this chapter. So unfortunately, there won't be any code implementation here. Um, but the issues that you should keep in mind is additive means things can be done in parallel, which is that's great. People love that. But there are all these implementation issues associated to how do I do the matrix vector multiplication for these preconditioners? And so yes, they're nicely additive, but then how do I do them efficiently? And the idea of doing things efficiently is you never ever, if you know there's a zero in a matrix somewhere, you never actually want to say, do that multiplication of zero times that element. Okay, so setting up a stiffness matrix that has lots of zeros in it and then doing in MATLAB matrix vector multiply sort of blindly is not a good idea. It's not efficient because MATLAB is not going to simply assume that when it gets to the zero, it should do something efficient. It's going to multiply zero times that number, and it's going to do lots of work to do it, perhaps. Okay. So you don't have to do that. So you want to take advantage of the fact that when I structurally have zeros in certain locations, I want to decrease my work. So that's a key point of all of this.